So let me first give a background. What is a two integrated reinforcement learning? So basically, you can say as we have a Q is a question, then model will reason. You give a model a question, and then your model reason the first action is 0, and the action till oh, maybe we need to search something, so they will ask for a to use, and the to use will give you a feedback, which is O. So in this way, like you are interact with the external tools to have some external information. So basically, if you use GRPO to train the to-use model, usually what we will do is we will mask the O, which is the feedback from the tools. The reason we want to, so you can see from the loss function here, you will only calculate the loss function on your action token, which is your model's own outputs. So the reason we want to mask the O, which is the feedback from tools, is because they're off policy to your model. So what is the off policy? The definition of off policy, which means if you send this document, this tool feedback into a model, and their likelihood on each token is low, which means they are not likely to generate such a sequence, such a feedback. So it is called off policy. So the off policy will make your training very unstable. So people usually mask those feedback token to train the reinforcement learning. And yeah, you can see here on the upper side, I show two figures. The blue one is you mask the feedback from your feedback during your loss calculation, and the orange line is you don't mask it. So you can see even with PPO, the training will fail. I mean, eventually. So this is the first unstabilization, but this is not the focus of this project. I just want to mention that there's such an issue, but this issue can be resolved by mask your feedback. But I mean, why? I mean, there's another issue. What is another issue? Because your feedbacks insert into your model, so that will make your reasoning have a huge distribution shift. So, for example, maybe your y0, which is your first reasoning, and then you search user 2 and got the O0, which is your first observation. And you continue to do the reasoning, which you obtain the y1, and this y1 will have a lower likelihood because due to the O0's distribution shift. So that will be our focus, and especially people found that if you train in tool integrated RL, the GRPO will fail after several steps, but PPO won't. So you can see from different model like 3B and 7B, and base and instruction tuned model, the orange line, which is the GRPO loss, they will collapse. So what's the mixture behind the GRPO's collapse during the tool integrated reinforcement learning? So this is a research question of this project. Maybe we can first start with an initial study. So if we reduce, the GRPO, you will roll out G responses and to calculate the advantage and do the IL training. But if you reduce the number of group size to 1, which means you only use a quick response to train your model, there's no negative gradient, which means there's no incorrect response participated in your training. Then your training is smooth. So this indicates that the claims originate from the negative gradient, from the incorrect response. So in this paper, we declare that the claims is introduced by is caused by the incorrect response, and it's introduced by a effect named likelihood displacement. And the likelihood displacement will make your training, make your generated response likelihood lower and lower. When your response is getting lower and lower, first, you will have a large gradient norm during the loss calculation. And the clip, the clip in your reinforcement learning cannot clip those negative parts. So that will make a very unclipped large gradient norm. So that's will make your training failed. But before the clamps, well, we observe 3 additional simpletons. The first is there's reward still already drops. Second is, yes, before clamps, there's already a lot of large gradients. And before clamps, your models already started to output some nonsense words. So let's say, to better visualize what we observe, we have this figure, GRPO, using GRPO to train a 3B instruction model on search as the tool. So you can see, and so during the training beginning, like the correct response likelihood, which is your generated response likelihood, is stable, but later gradually decrease. And when it's enter an acceleration phase, which means that the likelihood drops quickly, your reward start to drop, and the gradient start to significantly increase. And take a closer look. We measure this metric. We measure, okay, after one step update, how is the likelihood of correct response changed during your training? And you can see from the figure here, at the earlier training, it's okay. Most of all the samples, like their correct responses likelihood is increased, not decreased. But later, there are more and more samples whose likelihood is decreasing, which means that your models, because in reinforcement learning, they encourage the correct response and penalize the incorrect response. That means that so your negative responses likelihood is definitely will decrease. But here we show that not only the negative response, incorrect response will decrease in likelihood, but also the correct response will decrease in likelihood. And finally, your all responses likelihoods will reduce a lot. And you can also see the figure here that we plot the entropy. The entropy is a measure of your overall output confidence. If the entropy is higher, the lower your output confidence, or the lower your output likelihood. And we can see entropy exploding in the later of your model training. So why it is harmful? So you can see from this, if your model's output likelihood is very low, for example, they will have some nonsensical reasoning, because like all your tokens likelihood is because you are doing sampling, right? When you are generating next word, you are sampling among a vocabulary. But because your token likelihood is very low, so they're they're just a random sample some words from your vocabulary site because of the likelihood displacement issue. So that's why that will make before your clamps, that already make your model they cannot have meaningful reasoning. Yes. And to see why will this likelihood displacement happen, we made a simple demo, where we use the 3B instruction model to train and to do the GRPO training. And then the model will actually have 2 actions and 1 tool usage. So first step, they will reasoning and generate a search query. And then we will use the search query to have the feedback. And after the feedback, we will do another reasoning, which is conditional on all your previous contexts. So we show the likelihood of the actions before your 2 use and after your 2 use. So you can see in the early of the training, it's natural that the action likelihood after the feedback is lower than your action likelihood before your feedback, because if you insert a auto distribution external knowledge, that will make your model have a distribution shift, such later reasoning's likelihood will reduce. So it's reason. As you can see, as training goes to later, the first chunk of the first action's likelihood decrease more significantly compared with the second likelihood. So, but why it is like that? Because we observe there is a lot of, actions in your inquiry response. The first action of your inquiry response is actually correct. The why it is correct, because we can see that the green line is we check the match ratio with your correct responses, like first action. The match ratio is measured by if they reason the same search query. So that means that your first action is very similar to your correct responses first action. And our theory actually tells you that if you, because your GRPO can be regarded as a group level contrastive learning, the contrastive is within the correct group and incorrect group. So if your correct group and incorrect group is very similar to each other, so the incorrect group will have a large effect to reduce your correct group's likelihood. So that is why the first action drops more sooner compared with the second action, because your first action of incorrect response is very close to the actions in correct response. Sorry, the first action in correct response. So what we do is, we do a very simple regularization. Because we observe that the correct responses likelihood reduced after training. So then we add a regularization. This regularization, the first term will select the responses whose likelihood dropped after training. So just measure the likelihood and compare with its baseline likelihood, and then if the value is smaller than 0, which means it is decreased, and then we will activate it. And then second, we do a token level penalization, which means that within those reduced response, we will penalize those whose token that is reduced. And we will give those token an inverse effect, like to increase their likelihood. So in this way, we can design this simple regularization to avoid the likelihood displacement issue. And you can see, after adding this regularization, like first, the blue line is the original GRPO. The orange line is we add a small regularization, add a very small effect. You can train longer. And we add even a stronger effect, and you can train like more than 500 steps. So like train forever. So in this way, we kind of can stabilize the GRPO training by resolve the issue of the likelihood displacement. And we can see some performance. So here we compare with the results from Search R1, who only use GRPO and they report is failed. And we can say, the performance improves significantly. First, we actually have 2 datasets. The first training dataset is the NQ dataset. NQ dataset is natural question dataset, which is a single hop question answering dataset. The single hop means you only need to use one tool can finish the task. And we also have multi-hop. Multi-hop means, maybe you need to search more than once to answer the question. So you can see that here, our results demonstrate a consistent improvement compared with without GRPO, I mean, without our likelihood displacement loss. And then you can find, okay, even on the unqueued plus whole port dataset, we achieve like more than 31% improvement compared with the original GRPO training. And here because we haven't finished our task yet, but even we only train with natural creation, like the single hop creation data set, we can outperform the reported results from the search R1, which use both the NQ and whole port data sets to train the model. And we see a huge improvement here. And we also, I mean, we haven't finished the NQ plus whole port results for the 7 billion, but we have finished the NQ only dataset. And you can already observe a significant improvement compared with the reported results from the original search R1 paper. And we keep all the parameter consistent, like the same as the search R1 paper. So so that's all for today's presentation, because I didn't include any theory part in this slide, because it's kind of I don't want to make the presentation too complicated. But yeah, that's our project. I also appreciate Rishu's help during my develop this and finish this experiments. Yeah, it's a very heavy load task. Yes. So if you have any question, or if you have any question, please feel free to ask.